All right, good morning. Forgot I was on mute. So today we'll begin chapter 4, transient analysis. It's an extension of chapter 3 where we looked at the voltage and current for a capacitor and an inductor. Now, these are energy storage devices, right? We already established these are energy storage devices, and the voltage and the current for these components is a function of time. The energy transfer, of course, cannot take place in an instant, right? So what we are going to look at is the equations that govern this energy transfer phase, where the energy is being received by the inductor and the capacitor, or it's sent back into the circuit. Okay. All right. So first thing is about notations. We look at different circuits, each containing an inductor or a capacitor. But when we say it is one component, we are referring to the total equivalent value of multiple components in the same circuit. So you could have multiple resistors in the same circuit, and we reduce it down to one single resistor. We call it Req. Similarly, we can do so for inductor and capacitor, Leq and Ceq. Okay. So that one refers to the total equivalent value of that inductor or capacitor. So we could have Req, Leq, and Ceq. Okay, Ceq. If if we have a circuit with a resistor and a inductor, we refer to it as a RL circuit. Resistor and capacitor is referred to as a RC circuit. And resistor and inductor capacitor is referred to as RLC circuit. Okay, RL, RC, or RLC circuits. When we take a look at these circuits, especially the ones that have one energy storage device, one LEQ or one CEQ, we discover that it has a first order differential equation. Okay. So we are required to solve a first order ordinary differential equation. Hence, these RL and RC circuits are also known as first order circuits. Okay, first order circuits. If it's more than one, we have a second order differential equation, and hence it's referred to as a second order circuit. And then so on and so forth. For the most part, we are able to reduce it down to one single component, and so we refer it to as a first order circuit. And that's what we are looking at in this chapter. Okay, first order circuits. Now, when energy is being sent or received by the inductor or the capacitor, the charge in those components is building up slowly, right? That receiving the energy, charge is building up. Hence, when it's receiving the energy, it is known as the charging phase, charging of the inductor or charging of the capacitor, meaning those inductors and capacitors are receiving the energy, and when they send it back into the circuit, they are being discharged. So charging and discharging refers to the receiving and the sending of the energy. Now, whether it's being charged or whether it's being discharged, after a certain point in time, the value is going to reach a fixed constant state. Whether it's zero or whether it's max, it is steady with respect to time. So that phase is known as the steady state phase, and those values are known as the steady state values. But between these steady states, meaning before or after it begins charging and discharging, the value is fleeting, it is momentary. Every point in time has a different value for the voltage and current. It is transient, and hence the analysis is referred to as transient analysis. The value of the voltage and current during the charging and discharging phase is transient, and hence the analysis is also known as transient analysis. We are simply looking at the energy transfer process. So the value of the voltage and current during the energy transfer. And we'll look at both for RL and RC circuit. Okay. So as I was saying, once it reaches full charge or full discharge, it's steady state. The illustrations here are showing for charging phase, and you can see they have for both voltage and current, they have a similar form, which is exponential in nature. Exponential in nature. Since this is the charging phase, it is receiving the energy, and at some point in time, it reaches the max value. Okay. So the subscript notations we use here, and I will point it out. X-axis is always time, again, time dependent. We have time t equal to 0, meaning the point in time at which we begin our analysis. Begin our analysis. It is also known as 0 or I. The I stands for initial. So we could describe II or VI, or in some of the equations I have is I0 or V0. They all mean the same thing. The initial conditions right before we begin our analysis. Okay, right before we begin our analysis. So time t equals 0 at which we begin our analysis. Time less than 0, less than t equals 0, are known as the initial conditions. For the most part, all of the examples that we look at in this chapter will deal with a fully discharged capacitor or a fully discharged inductor, meaning there is no stored energy. So the initial conditions basically would say that VI and II are equal to 0. The chart illustrates some value, right? There's some value here for those current and the voltage. But most of the examples we look at, that II and VI will always be equal to 0. All right, and then it'll begin charging from that point on. And of course, after a certain point in time, it reaches a max value, after which it is at steady state. When the value of the voltage or current does not change with respect to time, it is always known as steady state. Okay, even the initial conditions, if the value is not changing, it is technically steady state. And then the time in between is when the response varies and it's transient response. And we'll derive the equations for that time period, the transient response. Now, transient response is of two kinds, natural and forced. And it's not as sinister as the word indicates. Forced is simply due to the application of an external input, which is all of circuit analysis that you have done so far. Okay, if you connect a source, to a circuit, the response in that circuit is referred to as forced. You connect a battery to a resistor, that resistor does not have voltage or current of its own. You connect a battery to a resistor, the voltage or current that comes out in that resistor is due to the externally applied battery. And so the response of the resistor is a forced response, which is what we have seen so far, right? So that forced is not as sinister as the word sounds. It's simply the application of an external input, which is basically charging of the capacitor or the inductor. Now, if you take a fully charged capacitor or a fully charged inductor and you remove it from the circuit, or the circuit changes or disconnects it from the source itself, and that capacitor or inductor starts discharging through a separate part of the circuit, then the response of the voltage or the current in that capacitor or inductor is inherent due to the stored energy. It is not due to the external application of an input. It is due to the stored energy. So it occurs naturally, and hence it is referred to as a natural response. Is everyone clear? Natural response refers to the discharge of the components. Forced response or step response refers to the charging of the components. So now we have two kinds of circuits, RL and RC. And then you have two kinds of responses, natural and forced. We have a 2x2 cross matrix, so we have 4 different circuits to look at. Okay. So we look at those 4 circuits, we look at the equations, and I will cover the previous 2 sections. I know I will be able to cover at least RL and RC natural responses. On Friday, I will cover the forced response, and then we look at the equations. We look at the examples, and then the homework will due on Sunday night, and then quiz on the following Monday. So open up the homework today. There are some short answer questions. There are some extra credit tutorials on there. At least get started on the short answer questions, the qualitative questions, and then quantitative. You can we'll look at the examples on Friday, and then you'll have Friday, Saturday, and Sunday to solve for those problems. All right. So natural response circuits will simply be an inductor and a capacitor in connection with a resistor. So you have a RL circuit and an RC circuit. And in both cases, the stored energy is simply being discharged through that resistor. Remember, I said the total equivalent capacitor or inductor simply notes EQ, or EQ simply notes the total equivalent inductor and capacitor. So if you are able to reduce it all down to one single element, it is still RL or RC circuit. And then if you add a source to this circuit, we get a forced response circuit. And this simply notes the Norton current IN and Thevenin voltage and Thevenin resistance. I'll come back to this reference, but for now, just understand that if you add a source to an inductor or a capacitor, it is a forced response circuit. These circuits, by the way, are, is the most simplest version for explanation purposes. Real life circuits are, of course, much more complicated. How many of you are taking the lab? Pretty much majority of the students. If you remember lab 5, procedure number 2, you had an inductor here. I'm going to skip the inductor. I'm going to draw out simply the capacitor, which are a bunch of resistors, and you had a 10-volt DC source. So if you all remember, what was the voltage across the capacitor? Very, very small. It was like 0.7 volts or something. If you apply 10 volts, do we expect 10 volts across the capacitor? No, because the voltage or the current that's being supplied by the source will be dropped across all 3 resistors. Not the last one so much, just because, well, actually, no, even the last one is included. Even the last one is included because the current actually charges through that resistor. So all 3 resistors are involved in the charging and the discharging phase. So how can we determine the voltage that is being applied to the capacitor? By finding the Thevenin equivalent circuit as seen by that capacitor. And that is one of the other applications of Thevenin and Norton. So If you all recall, I did mention that there are multiple applications where we need Thevenin, and this is one of the prime reasons why. Because if you have a circuit, even a simple circuit like this, that has 10-volt source and 2 or 3 resistors, that 10 volts is not directly applied to that capacitor. We have to determine the Thevenin equivalent circuit as seen by the capacitor. Oh, that might drawing. Source, resistor between A and B. And hence, the circuit diagrams on the left all mention the Thevenin voltage, Thevenin resistance, or the Norton current. Okay, so it's a simplified version of the circuit. That VTH and RTH could represent hundreds of resistors, hundreds of sources. But we represent it as one single source by finding the Thevenin equivalent voltage and current. And that is the circuit that we will analyze. Does that make sense? Right? Now, you can be rest assured, I'm not going to ask you something like this in an exam, or, not directly. I won't give you like a new circuit and say, just find the Thevenin, find the voltage. So let's look at RL first. As I mentioned, we have 4 different circuits to look at. I'd like to cover at least the 2 natural response circuits first. So the concepts, if you look here, the concepts that you need to familiar with, starting with the switch first. Okay. On the face of this, what do you think this means? We have the time listed, t equals to 0. That can simply be the moment in time at which we begin our analysis. Right? T equals 0 is the moment in time which we begin our analysis. There is an arrow that flips up. And so it simply means that at time t equal to 0, the switch was flipped open. Okay? And this is a very important concept in transient analysis. At time t equal to 0, the switch was flipped open. And logically, it follows that prior to time t equal to 0, the switch was actually closed. Okay? So if the switch is being flipped open at time t equal to 0, then prior to time t less than 0, the switch was actually closed. Okay, so time t equal to 0, switch is flipped open. Time t less than 0, the switch was closed. Those are the initial conditions. Then we write down the values for the voltage and current. So if the switch was closed, the current source has a pathway to flow through the inductor in this direction. Okay, what happens to the inductor if the switch was closed for a very long time? What happens to the source energy? A very long time simply means that the inductor is reached at steady state. It is fully charged. When it's fully charged, the inductor behaves like a short circuit. And so all of the current is simply flowing through that inductor. Nothing is flowing through that resistor at all. Okay. If the inductor is a short circuit, all of the current is flowing through the inductor. Nothing is flowing through that resistors. Again, not a real life circuit right now. It's simply a very simple explanation circuit. All right. The inductor has reached full charge. Once the switch flips, the circuit looks like this. The switch flips open. The source and R0 are disconnected from the rest of the circuit. Right? The switch flips open. The left side of the circuit is no longer part of the inductor. The only thing left in the circuit is the inductor and resistor R. You have a fully charged inductor, you have a resistor connected to it. All of the energy of the inductor slowly discharges through that resistor. And so the current flows through that resistor. So now it is our job to establish the values of the initial starting current. The initial starting current, in this case, depends on the maximum charged value. So here's where the concept comes in. We know that the current through an inductor and the voltage across a capacitor cannot change instantaneously. So here we use the concept of T plus and T minus. Okay. Do you have a question? Okay. Plus indicates right after or immediately after and minus indicates right before or immediately before. Plus is succeeding, minus is preceding. We know that it cannot change instantaneously, so we can write that the conditions at time t equal to 0 plus and 0 minus are exactly the same. Because remember, we have no source here. So we need to establish what the current is. And we get that value from the time before the switch was flipped. Before the switch was flipped, which is 0 minus, the value, the initial condition, the initial value of the current is equal to the source IS. Yes. Yes. Yeah. Yes. So that's why the source is actually going down. Again, for explanation purposes, but that's why the source is shown going IS this way. And so inductor would charge up the other way. And then when it discharges, it also goes in that same direction, plus to minus. Yes. So the value of the current to the inductor at 0 plus, which is right after the switch is flipped, is exactly the same as the current right before the switch was flipped, which is 0 minus. And we refer to that as I0, the initial value of the current, or II. And that's equal to the maximum value, which is the source current IS. So inductor has IS, now trying to discharge through that resistor. All right, any questions? So this is the circuit setup that you'd have to do before you begin your analysis. Okay. To write the equations for the voltage and current, we apply KVL at the top. We have VL plus VR equals 0. VL, inductor voltage, is L di over dt. Resistor voltage is simply I times R, V equals IR. And we have a first order ordinary differential equation. Job as engineers is to find a solution for this first order equation, which is not my idea of a good time. Thankfully, greater minds have come before us and they solved this and they obtained the solution for this equation as I of t is I0 times e raised to minus t over tau. Okay, let's look at each of these components individually. This equation simply describes the current for an inductor as a function of time, I of t. Okay, it's made up of two separate products. It's I0 and it's e raised to minus t over tau. I0 and e raised to minus t over tau. I0, of course, is the maximum value. So if I was plotting I of t, this would be I0, which is equal to Is. That's the max value. Okay, max value. So at t equal to 0, the inductor current has a maximum value of I0. Then you have an exponent, e raised to minus t over tau. Tau is the Greek letter tau, is known as the time constant. And it actually is a constant. The unit is seconds, but it's given by the equation L over R. It depends on the size of the inductor and the size of the resistor. Okay, L over R. So it is always a constant, and the equation is the same whether you're charging or whether you're discharging that inductor. L over R. If you plug in t equals 1 tau, you obtain e raised to minus 1, which comes out to be 0.37. So after the first time constant or has elapsed, the value of the current drops 63%. So let's see. 6, so about right here. And then, of course, exponent form. This data point is about 0.37 times I0. 63.21% of this value is lost immediately after the first time constant. Again, it's exponential in nature. So it doesn't matter whether it's charging or discharging, whether it's a capacitor or an inductor, it always loses 63% of its value after one time constant. When it's charging, it has the exact same equation. It acquires 63% of the total max charge after one time constant. Okay, that's the meaning of those equations. So it loses 63.21% and drops down to 37% of its max value after one time constant. And that's why we have that kind of chart. So I0 into e raised to minus t over tau. Mathematically, t can take on any values, right? It can take on any values. You can plug in t as 1 million seconds, and you would still obtain a value for I. I at time t equal to million seconds would be like 0.0000000, multiple zeros, and you still have some digits at the end. It'd never be finitely zero. So quantitatively, you could say this equation would never end. Real life, of course, it will go to zero. But we put a stop to it by generally accepted convention. We put a stop to it after 5 times tau, because the value is less than 1%. Less than 1% of the value is left. So we say it's fully discharged. And if it was charging, we would say it is fully charged. So 5 tau, 5 time constants, we consider it to be either fully discharged or fully charged. Okay, I of t is I0 into e raised to minus t over tau. You don't have to memorize these equations, but after you see them for a while, they'll become second nature. You can have them on your equation sheet, but you should be able to recognize the problem and know when and how to apply these equations. The equations for the voltage, power, and energy have the same form. V equals IR. So V of t is simply I of t times R. We plug in the values for I of t, the equation in there, and we obtain the voltage value at any given point in time. Similarly, power is V times I, or I squared times R. And so instantaneous power P of t is I squared t times R. Okay. Total energy dissipated in the resistor is the total energy that was stored in the inductor, which is half Li square, which is what we have here. The total stored energy in that inductor is all released through that resistor. So it's half Li square. Make sense? All right, any questions? Any questions on the equations? Nope. All right. Well, then let's look at natural response for a RC circuit. Similar model. We have a switch that is being flipped at time t equal to 0 from A to B. When it's connected to A, the capacitor is connected to the voltage source VG. It charges up. The capacitor voltage VC is also equal to VG. The G in here simply refers to a generator. It could be VS. It could have a value of 5 volts, 10 volts, could be anything. But the point is that sufficient time has elapsed, that the capacitor has reached steady state, it has reached full charge, has a voltage of VG. Once the switch flips, the source and R1 are disconnected from the circuit, and the circuit is redrawn and looks like this. Okay. Now the capacitor is simply discharging through that resistor. All of that stored energy is being discharged to the resistor, exactly the same as the inductor natural response. So, initial conditions, we can dictate voltage across the capacitor right after is the same as right before, which is VG. If you want to write an equation, we apply KCL at the top. We have IC plus IR is equal to 0. Capacitor current IC is C dV over dt. IR is V over R. Once again, we have a similar first order ordinary differential equation. We solve it, and we can derive a solution for it that has the exact same form as the one for the inductor current. V of t is V0 into e raised to minus t over tau, where V0 is the initial voltage, Vg. The time constant is simply the product of the resistor and the capacitor. Very easy to remember. For RC, time constant is R times C, RC. And that's it. When we plot this, we again obtain the exact same expression. Oh, sorry, not expression. We again obtain the exact same curve. So V0 is max. After 1 times tau, it drops to 60%, 2, 3, 4, 5, and 6. follows the exact same path. So it doesn't matter whether the capacitor is small, large, multiple, doesn't matter. Charging and discharging always have the same exponential form. Okay. Equations for the current, power, and energy. Again, I is V over R. So I of t is V of t over R. Power P is VI or V squared over R. And so P of t is V squared of t over R. The total energy discharged in the resistor is equal to the total energy that is stored in the capacitor. So it's half CV squared. Half CV squared. All right, any questions? Does the equation make sense? How to use, how to apply the equation? Any questions? Okay, then one final summary slide. If you're doing a natural response, the first step is to identify the circuit. Look at the point in time at which you have begin analysis, see when the switch flips, redraw the circuit, and then reduce. Redraw the circuit and then reduce. Reduce is basically reduce to one single EQ component. Actually, should be lowercase. Okay, so redraw the circuit after time t equals 0 and then reduce. Establish the initial conditions and find the value for the current and the voltage for the capacitor or the inductor. Once you have the component values, you can find tau. And once you have tau and I0 and V0, simply plug it into the equations. That's it. And that would give you the voltage and current equations at any given point in time, that transient period. You only need to find two values: the maximum initial stored voltage or current, and then the time constant. And that's it. All right. Pause and questions. Any questions? All right, we finished early. All right, so I'm stopping here because the previous two sections, I stopped at this slide. We finished, we only had enough time to finish at this slide. So again, as a reminder to all students, the topic has been introduced. You should open up the homework. Today is Wednesday. You have, well, at least I would say half the day, if not more. And then Wednesday, Thursday, Friday, Saturday, Sunday. Sunday night is when your homework will be due. I will cover the other two circuits, which is the charging phase and then the example problems on Friday. All right. I'm available for questions after I stop the recording. All right. So we'll stop right here, and then I'll see you all on Friday.